So to get started, we'll look at the slender wall design, which is the inherent part of the enclosure of a tilt-up building. And it all goes back to the slender wall method, which is in the ACI 318 code. And it allows walls to be very, very slender. From a background looking at the provisions of this method, it hasn't always been in there. There's two other methods for designing walls. One's the empirical design method, and another one's designing it as a compression member, but they don't allow slender walls. The slender wall method allows very slender walls with some important restrictions. Number one is there's a P delta effect, or the second order bending effects, that turns out to be very important, as well as the eccentricities that are loaded. If we have a load at the top of the wall that is eccentric, it creates secondary moments or that are also very important. We also have very special limitations. The sections have to be tension controlled so that we can better anticipate its behavior. The axial stress is limited, and so are the deflections. Since we have very slender walls, we want to ensure that we don't have excessive deflection. So I'll be touching upon these as we go through. Our order of presentation for the slender wall design is going to be looking at the historical development of this section of the code. We'll be comparing the old ACI 318 to the new ACI 318 because there was a dramatic change several code cycles ago that's important to understand. Also, we'll talk about the reason for this dramatic code change, which will help you understand why the code has changed so dramatically after several code cycles. And then I'll provide an example that will run through this for the slender wall. And then we'll have our break, a 5-minute break with 10 minutes of questions and answers. So starting in our historical development, if we take a look at a typical tilt-up wall building with their concrete walls, and for a while before the slender wall method was really in the code, engineers were experimenting with different ways of making these very walls so slender. They were using a lot of second order effects and provisions that really were suspect to some plan checkers and some engineers in the field. And so there needed to be a codified method or some sort of agreed upon method, and it was first taken upon by SEOSC, the Structural Engineers Association of Southern California, in conjunction with the Southern California chapter of the American Concrete Institute, to develop some provisions that were simply looking at this type of building stock and once and for all to determine whether there was any limitation to the slenderness on these. There were previously some height to thickness ratios that were extremely limiting to the type of construction. The work was done in the early 80s by an all-volunteer group, volunteer materials, volunteer engineers, and it was a combination of concrete tilt-up as well as slender masonry walls as well. And that is why you'll see many times the slender wall provisions of concrete and masonry tend to be very similar, as they all go back to these original full-scale tests that were done in the early 80s. The tests were done on a rig or a jig that was composed of a large test frame with a airbag to provide a pressure to the test panel. The test panels were about 4 feet wide, and we had full-size test panels that were also loaded with a loading drum that provided an eccentric load through a lever at the top of the panel to mimic as best as possible the types of loads that these panels were seeing in the field as they were being designed. A pin connection at the bottom was modeled, and the airbag was filled with air, and the pressure regulated, and the deflection was measured to watch the load deflection characteristics of these. There were 30 walls that were tested, both concrete and masonry. 12 were tilt-up concrete panels, which were the slender walls. There were 24-foot vertical clear span. There were of varying thicknesses. There were 3 panels of each thickness here, from 4 3/4 to 9 1/2, and these thicknesses were selected specifically to meet certain height to thickness ratios from 60, 50, 40, and 30, with the idea to determine if there was some sort of limit where these panels would buckle and become unstable. These were 48 inches wide. They had 4 number 4 vertical bars. The concrete and the materials were tested to determine their properties so that an analysis could be done accurately. As they were tested, there was significant deformations that these panels were able to take. The tilt-up walls deflected up to 13 inches at yield and 9.2 inches at ultimate. And ultimate was not an instability, it was simply where there was no more load able to be applied to these panels from the airbag. We reached the full limit of the airbag at this point. And there was no instability determined at all during the maximum displacement, even though there was the roof load at an eccentric distance. This really showed that there was no limit to the height to thickness ratios, that these flexural sections behaved in a very predictable, forgiving manner, even when completely cracked, as you see there on the left from the slender wall. On the right is the masonry wall specimen.